All right, let's do part B. Welcome back, and let's try and see what happens when we have two different indices, right? Two different, ones that have two different indexes. So we can have something that looks nice. So we're gonna, we have something that we know can work, is that we can use the radical property, and we'll see what this means in a moment. So if I have the root of x to the b a, is also equal to the root of some constant AC to x to the BC. And what that means is that I have BC over AC, and I can simplify this down, and this just becomes x to the b over a. Now, why do we want this step here? Like, what's the advantage of having the BC over AC? And we're going to think of like exponents. We're going to think of sort of like common denominators, right? That we're going to want to get denominators of the exponents the same. So we're going to kind of think about it like that. And the best thing to do is radical notation. I'm going to put 7 somewhere else. So radical notation to exponent notation, right? So we want to use exponent notation where we can, much more powerful, right? So we want to write it with exponents where possible, much more powerful, more reasonable. So what does that mean? Well, if I have the fourth root of x squared, what that really is, and I'm just going to say for all of these, x and y greater than, I don't have any. Do I have any y's? Yeah, I'm just going to say, for these ones, I'm just going to say x greater than or equal to 0. I can just rewrite it with exponents x to the 2 over 4. Well, that simplifies down to x to the 1/2, right? So I've just done that, made it simple, nice and easy to do. Works out super well for us. And I prefer this method the most, right? So that's the number 2, return it from radical notation to exponent notation. Using method 1, we'd have to cook up a half or something like that. Now let's see the real power of this with x cubed times the cube root of x. And this is something that's like, oh, different bases, different stuff. What's going on here? Well, or the bases are the same, but the exponents are different, so we can't really do a lot with them at first glance. But we can rewrite it as x to the 3 over 2 times x to the 1 over 3. Well, what we do know is that if I have a to the m times a to the n, that's just equal to a to the m plus n. Nobody said those numbers have to be integers. They can also be rational numbers. So as I do this, I'm going to say I'm going to have x to the 3 over 2, x to the 3 over 2 plus 1 over 3. But adding fractions, we do know that we need a common denominator. So what's going to happen here is 2 and 3 make a common denominator is 6. 3 times 3 is 9, so that's 9 over 6. And then 2 times 1 is 2, plus 2 over 6. And we're going to get x to the 11 over 6. So that's what it is as a single radical. And now I did this in my Math 10. I know because I have it as a test question right now. So it's to the 11 over 6. I guess if you want to simplify the radical, you would still have 6 x to the 11, and an x can come out as x, and I would have 5 left over. You can do that too, right? A group of 6 will come out and just be x on the outside. So be mindful of that. That's possible as well too. Either way, it's totally okay. If you look at it as fractions, right, you can also see it with fractions as x to the 6 over 6 times x to the 5 over 6. Oh, I know 6 over 6 is 1. So this would be x to the 1 times x to the 5 over 6. So that works too. Both mean the same thing. Okay, let's look at 9. So 9 is same thing, but we're going to divide. Our x's are still greater than 0, so we don't need to mess around with absolute value. So we're going to take x cubed, and we're going to the root of x cubed and divide it by the cube root of x. In this case, right, we're just going to rewrite it. This will be x 3 over 2, and this will be x 1 over 3. And the rule is if that I had am over an, that these two would subtract, m minus n. So I would do that with this as well. So I have the same base, 3 over 2, minus 1 over 3. Same numbers as before, so I'm going to get x to the 9 over 6 minus 2 over 6. And this is going to get x to the 7 over 6, or x times x 1 over 6, or x times the 6th root of x, like that. Right? So there's a few different ways that we can write it out. But really, it's paying attention to what's happening in the exponent here and simplifying the exponent down. So we're good with that. Let's do a couple more, and then we'll have like one more video that we're going to take a look at here. So number 10, we're going to do example 10, and we want to simplify root 2 over 7. But we're going to use a process called rationalizing the denominator. So we're going to do something called rationalize. So if you want to look this up or look in your book or use the index in your book, rationalize the denominator. And what that means is rationalize the denominator. And what this means is no radicals left on the denominator. So there's no radicals on denominator. And you're like, well, Mr. Van Dyke, there is a radical right there, that's 7. I can see it. You're telling me you can get that radical to go away? I'm telling you can. So we will get rid of that denominator. You will see it leave. So no radicals on denominator. So as we do this, let's take a look. I'm going to separate this out, root 2, root 7, like that. So I'm going to use my rule where I can say, well, my first step here is I'm going to put a radical on the numerator, radical on the denominator. But I do know this property, that if I have a radical of a and it's a square root times a square root will just have the original thing coming out. So what I can do is give this a factor of root 7 multiplying by top and bottom, because I know, note, that root 7 over root 7 is just equal to 1. So I haven't changed the value of the number, I'm just changing how the number looks. Now I'm going to have on the top here, I'm going to have 14 on the top, and I'm going to have root 49 on the bottom. Well, that root 49 is going to become 7. So now, no radical left on the denominator, right? So no radical on denominator. And this has so many uses that we'll see in simplification as something that we're going to use over and over and over and over again. So just be mindful that this shows up repeatedly. So rationalizing the denominator is super important. It will be an expected step from this point forward. Let's look at 11, and then we will do part C. So cube root 2 over y. Actually, we're going to do 12 as well. So same thing here, but now I have a cube root. So what I have to do is that this is to the 1, this is to the 1. So to break anything out, I need it to the 3. So what I'm going to do here, if I want to get rid of this y on the denominator, I'm going to have to multiply it by the cube root of y squared over y squared. And what's going to happen, this is still going to be 1, and I know that y is going to be greater than 0 here. Well, actually, we can even say y just can't equal 0. That's fine, right? Because I can't divide by 0. But this whole thing is going to divide out to be 1, right? So I'm going to combine my cube roots, and I'm going to get 2y squared over y cubed. But now I can take this apart and say I'm going to have the cube root of 2y squared all over the cube root of y cubed. Well, that one on the bottom just gets to be y, right? The cube root of y cubed is just y. So on the top, I'll get 2y squared, and on the bottom, I'll just get y. Wonderful, wonderbar, right? So this is just saying now this note needs as many groups as index, right? So it needs as many groups as index. So if this was to the 4, if I had y, let's make it 5. If I had this, if I had x over y x squared over y like that. To break out a 5, I need to multiply it by y to the fourth over y to the fourth to get this bottom piece to be y to the fifth to break that out, right? So it just needs to be the same amount as the index. Okay, last one for this part, and then we'll finish, we'll start the last section. So I have the root of 5x over the fourth root of 5x over the fourth root of 10x cubed. And before I even begin, what I'm going to do, I'm not going to rationalize the denominator right now. I have fourth root, lots going on. I'm actually going to simplify my fraction first. I'm going to find some synergy that makes my life easier. I can use smaller numbers if I simplify this first. So before I even learn to use the new thing I learned, I'm going to simplify where I can. Well, 5 and 10 have a common factor of 2, and x cubed have a common factor of x. So I'm going to remove an x, and I'm going to remove a 5. Sorry, 5 and 10 have a common factor of 5, not 2. And so I removed an x. So the only thing left up there is 1. On the bottom, what's left is 2, and this is going to be 2x squared. Okay, now I want to get rid of both the 2 and the x squared. But this is going to be a little finicky now because we're going to have to be very careful. Because this 2 is 2 to the 1, and that x squared is x squared. So I need to get both to the fourth. So 1 plus what is equal to 4? Well, that needs to be 3. So I need to introduce 2 to 3, and 2 plus what is equal to 4? Well, that's 2. So here's what I'm going to multiply both by. I'm going to multiply both by 2 cubed x squared. 2 cubed x squared. And I'm doing it like this, so that way that 2 gets to the power of 4, and that x squared gets to the power of 4. Let's see what happens. So this will be 4, and this will be 2, let's call this 8x squared. No simplifications there. And we're going to call this 2 to the 4, x to the 4. Well, that has simplifications, right? So this will be 8x squared, and this will just be 2x, and that's it, right? So the that has been simplified there, so that way the numerator has a radical on it, but the denominator is radicalless. We've removed all radicalization from the denominator. Good job. We did forget, or I forgot, not we. I forgot that 4 there, but I remembered it for all the 3's. Good. All right, one more lesson, and that's it for 1.6. A lot of information here in 1.6.